Hello, welcome to the video on the assembler. This video focuses specifically on the line assembler I wrote. It's my first attempt at writing an assembler, and all it does is it takes a string that is input, it parses it, it checks its validity, it looks up the opcode in a table, a couple of arrays, and then it puts the opcode and the operand into memory. The first thing what I did was, when I looked at the assembler, was to think, well, got to actually look at how the 6502 instruction set is formed, and what the sort of legitimate, if you like, syntax looks like. And in its basic form, the syntax is just a mnemonic. So, for example, you can have an implied instruction or an accumulator instruction like CLC for the clear the carry, and that's just a single byte mnemonic. So that there, the mnemonic on its own could just stand alone. So anything here in yellow is an option, and anything, the operand is only valid on with some mnemonics, and again anything in yellow is an option depending upon what the operand is and what you're trying to do with it. So if we look at a couple of these examples, we've got LDA with the contents of address 5, so that would be a 0-page operation. The assembler would see that as a 0 page because it's only got 1 byte here. So as you can see, it fulfills the criteria there. It's got a mnemonic and it has got the optional, well, semi-optional operand. In this case, it's a non-optional because it's needed for the mnemonic. This is again also valid. So what we're saying is load the accumulator with the immediate, because the hash says immediate. The hash is optional. The percentage sign here says binary, so load the accumulator with that binary value. This is an STA, so a store accumulator into the hex address of C000. Again, you can see that works. And this ADC, well, this ADC is one of the index ones, indexed indirect, I think. And that's got the brackets, and it's also got the dollar sign for to say that this is a hex value. So in this case, we've also got the comma and the Y, and the other one, which is indirect index, is one way around or the other. I always get them confused, but I know what they do. And this one is saying take this value here, which is 92 in decimal. So the address of 92, offset it with the index register there of X, and perform the subtract operation. So all of these are valid syntax. So what the program does, the program actually uses a 15-bit flag, and we use quite a lot of binary comparisons and binary manipulation. So things like we've seen before, where we use the OR to set a bit, and the and then not and to clear and check bits and things. We don't use any recursion. The recursion is where a function calls itself, or a function calls another function, which calls the calling function, and kind of goes flip-flop round in circles. Compilers use it quite a lot, but we don't use it at all because it's a bit confusing, and I wanted to keep my code quite simple. So we all we do is we get the mnemonic from the input string, and we presume that the mnemonic is the first value passed in, the first sort of set of characters, if you like. And the delimiter is a space or a new line or a null, and that's pretty self-explanatory. So if you hit a space, the chances are you've got something coming after it. If you hit a new line, it's a single line. Hit a new line or a null, that is, it's a single entity. It's a single byte operation like CLC. And then we check the flags for the first time, and the first time in, we're looking for any of these sort of the hash and the dollar sign and so on, because they are the things that we're expecting to see, and we set flags accordingly to these. And the flag, the part of this 15-bit flag up here, we set them at this point. They'll become a little bit more apparent later on. Then we go and get the operand. And the delimiter for this is a space or a closed bracket or a comma. So you think about what we just saw in the previous slide. We're looking for things that can come after the operand, and then we check and set the flags for the second time, and we're looking specifically for whether any of these exist, and if they do exist, then we set various flags according to that, because obviously you're looking for setting things like indexed or indirect, or trying to make it pretty clear for later on when we actually come to do the interpretation as to what as to what addressing mode and what you need to do, what we need to do, with the operand and the and the opcode, and how big it is as well. So if it's 1 byte, 2 byte, or 3 bytes. So then we convert the operand itself from a string into a number using this string to long, which we've used before, standard one of the standard libraries. Then we set the flag based on the X and Y indexes registers, and that's only if needed. So if they don't exist, we don't set them. And then we go and get the opcode based on the addressing mode, and then set the flags again accordingly. So what we do is we look at the instruction length. So we say, is it 1 byte, 2 byte, or 3 bytes? And the opcodes and the addressing modes, they're configured in an array. So if there's no error at this point, then we say fine, and we go and put the opcode and the operand into memory, and the flags are used to determine how long the instruction is. So the process works like this. What we do we take a string that's passed in from to the assembler from our input code. In this case, it's the add with carry for the immediate value of 5. So we add this command would add the value of 0.5 to the accumulator. But our assembler doesn't know that at this stage, and what we have to do is we have to go along and pass this. So the first thing that happens is we set up some pointers. So we have our end pointer, that's what NP stands for. This is the one that walks the string. We have a copy array, it's called copy, I think, and our copy pointer points to the front of this temporary string here, and so does our mnemonic. And at the moment, the operand pointer doesn't point to anything. So what happens then is we go and we walk this string to get the mnemonic, and to do that we just use a very simple loop looking for the delimiter as we discussed in the previous slide. And the delimiter here is either a space, a null, or a new line character. So we start in there. So we look at the contents of NP, and the contents of NP is pointing at location 0. Contents of NP is A, so it doesn't equal any of those. So therefore we walk into the loop. Now, what this loop then does is it says take the contents of end pointer, turn it into uppercase, and put it into wherever copy is pointing to. So this is here, end pointer, contents is A, turns it into a capital A, sticks it into where copy is looking at. There it goes. Then it runs the plus, which is increment the pointers, and now therefore end pointer is pointing at location 1 and copy pointer is pointing at location 1. So the loop continues up until it hits one of these conditions, and in this instance it's hit the condition of a space. And at that point what happens is the loop terminates. Alright, and so there's a couple of things that we need to do once the loop is terminated. So we know that we've now got our mnemonic because we've hit our delimiter, and the delimiter is a space. So now what we say is, well, actually we need to terminate that particular string in our copy with a null and increment the copy pointer. So we do. So there goes the null, and the copy pointer now points at location 4. What we now do is we point the operand pointer at the copy pointer to say this is where our operand is going to start. Because what we're effectively doing in our temporary string here is we're creating a list of null terminated strings with various pointers pointing at them. It's pretty much how string talk works, but I wanted to have my own function to do it with my own pointers, so I wrote the routine myself. And so now we've got a mnemonic which is null terminated, and we can actually use printf to print that if we wanted to, or we could use any of the other standard functions because it is null terminated. But we can also use our own functions and check for null terminate as well. And our second part here now is operand is pointing at location 4. Now what we do is we ignore any other white spaces, and then we go into that bit where we say we set the flags for the first time, and we've only shown the first 10 bits of the flag at the moment because it could become a bit overwhelming, a bit too much for the screen really if we've got all of the flags on there. So we have a look and the flag says, oh yeah, we've got an immediate, so we'll set the immediate flag, and we've got a hex there, so we'll set the hex flag and we'll walk the end pointer on to pass that point. So the end pointer now points at location 6, and location 6 is carrying the string representation of the number 0, but it is a string there, not a number. So 05 is actually 05 in ASCII, not a number. Okay, notice that the copy pointer hasn't moved and neither is the operand pointer, but we have actually set the two flags at this point. Now, what we now do is we say, okay, it's not a single byte instruction, so we make sure that the single byte instruction is clear, because it isn't one of those. Sorry, the single byte instruction bit in the flag, that is. And then what we do is we walk the next loop, which says, okay, now look for these next part of the delimiters, which we saw in the process slide. So in the next part of the delimiters here, as a comma is added, the null character, the new line, or the close parentheses, close bracket, and we do the same things we did before without using the 2-upper, because we don't need a 2-upper in this case, and we just put the contents of the end pointer where the end pointer is looking into the contents of the copy. And so therefore 05 gets added to those two string locations, and then we null terminate the copy flag as we did before to create a string. So therefore now operand is pointing to a legitimate string that can be used by any of the standard libraries or any of the custom stuff we write. Now we look at the decision making at this point, because we've actually parsed our string. We've got rid of, we don't need the source of it anymore, because we've taken out of it what we need. So we've got ADC05, and we've got the various flags set to be able to say what that what this actually represents, and it represents an immediate command with a hexadecimal value. Okay, so at this point what we do is we convert that 05 into a real number. So we take the operand value and we turn it into the number 5, and it would do that. We've seen that happen with the standard libraries before, with the string to long. So you can pass in any number, and as long as you know what that is, and we do know what that is because the hex number is set here, so we tell the string to long that it's a hex value we want it to convert, and it converts it quite nicely into the number 5. Now at this point we move into sort of like a sub-step really, and what we do is we move into the flags the second time, and we say, okay, can we make some decisions as to what the addressing modes are using the various flags and all the various bits and pieces. And this is the second set of the flags, the top half if you like. Sorry, no it isn't, not at this stage. So the immediate flag is what we're looking at the moment. So yeah, we can make a decision based on that, because we know that we've got a 1-byte operand. So because it's immediate, therefore the whole instruction must be 2 bytes long, opcode and operand, right? So we've got the opcode for this, which we'll work out in a minute, and the operand is 1 byte, and it is because it's a number 5. Then we go and look it up. So what we're actually saying at this point is we use the 2 arrays that we've got set up in the assembler, and I wrote just added all these instructions, and these are null terminated strings in this mnemonic array, and there are 56 of them, 0 to 55, because there are 56 instructions in the 6502 legitimate, non-illegal if you like, legal instruction set, and therefore the add with carry is the one we were looking for. So what it does is it just says, look, we'll set our index to 256 because we know 256 is an illegal number, because the index can't be 256. All right, not considering there aren't 256 codes. There are only 255, right? So we walk a basic loop. We say from the start of this array to the end of the array, go compare what we've got in our mnemonic pointer, which is an null terminated string, with what we've got in our array, which is an null terminated string, and if they match, i.e. if the result is 0, then set the index to our current loop counter and break out the loop. So our index now becomes our index into our second array, if the index is less than 256, therefore if the index is valid, because we've set it, then what we do is we go fetch this little bit of maths here, which is the way that pointer, the way that a two-dimensional array works. So I don't bother with two-dimensional arrays in C. I just do it this way because that's how the compiler would do it anyway. So what it does is it said take your index, and our index in this case is 0, times it by 11. Well, 11 times 0 is 0, so we're working on the 0th part here, and then I add the addressing mode. Well, lucky for us, the addressing mode is 0 as well, so 0 add 0 is 0, so therefore we're working on the 0th element here, which is effectively the first element in the array. And if you think about it, that would actually work no matter what we did, because if we were working on the next instruction down, which would be the AND, which would be here, then that would be at position 1. Well, 1 times 11 is 11, so all of a sudden you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here, and then all you're doing is adding the addressing mode. Well, the addressing mode would basically take you up to here, and the next time you go around you do it again. So that is in my opinion a lot more simpler than dealing with two-dimensional arrays in C, because they're a bit convoluted. Okay, so at this point our assembler has actually got the two actual numbers that matter, the 69 and the 05. So we know that the representation for the ADC immediate in hex is 69, and the opcode, the operand is 05. So then what we do is we go round basically, and we set some of we check and set some of the remaining flags, and these are the remaining flags. So we've actually got an error flag, is flag number 12, which is in position number 12, which equates to 4096 in hex. So the first thing we do is we say, well, if we've set our error flag anywhere, then we print bad opcode. In actual fact, I've actually changed that. It just prints error these days because it's not necessarily an opcode fault. It could be a syntax error, so just print error. Else, it's not an error. So therefore, what is it? Well, is it a single byte instruction? So is it one of these? Yes or no? Well, in our case, it's not. Is it a 2-byte instruction? Because there's where our 2 byte is. Look, and 8192 relates to bit 13 there, and it says I've got to do an additional check here, because if the location is greater than 65534, bearing in mind we've only got 65535 memory locations, we can't fit a 2-byte instruction into the remaining memory, because 65535 and 65536, well, 65536 is an illegal memory location, so you tell them that. Otherwise, you go and pop the opcode and the low byte, which we set earlier on. It's actually set in the code. We've not explicitly said that here, but it is. And that's how we pop it into memory. And we do the same thing for the 3-byte ones there. And notice the ++ on the end here, because that's how the assembler then returns the location and passes it back to the assembler. So therefore, if it's an error condition, location never gets increased, and therefore what it passes back is the same as what it passed in, and you're left on the assembler. You're left assembling on the line you were left at. We'll demonstrate that in a second. Okay, so this is the emulator as it stands now with the assembler in it. So the way the assembler works, we demonstrated this in the last video, but we'll demonstrate it again now. So if you've got a single byte instruction, you put CLC in there, and it says, yep, that's fine, we've got a single byte instruction. But if we put a bad instruction in here, so if we try and do something silly, for example, like CLC 00, like that, okay, it'll come up with an error. Now, I noticed several things. First of all, when we did the original CLC, the byte calculation was perfect. Okay, I can't quite remember where I was up to, so I'll start that bit again. The the bottom line of this is that the CLC here is a valid command. It's a 1 byte command, and the assembler has taken it from AAA 0 through to AAA 1, which is 1 byte increment. It's taken one look at this command and it said, I don't think so, because that's an invalid command, and I've thrown you an error, and I've given you back the address of AAA 1 because I need you to put something valid in there or stop assembling. Now, the way that the assembler works out invalid code is if we go up here and have a look at the code, what it does is it looks at this here, this which is the mnemonic opcodes, and it says if I get an FF back, then I know you've typed something rubbish because there's no addressing mode for that opcode. So if you look at if we try and do this out for CLC here, so let's see, where's CLC? CLC is there, okay, and CLC is what is it? 1, 2, 3, 4. It doesn't matter actually because I'm thinking about it. I put them down the side here. So there's CLC, okay. So I commented it out. So it goes and looks up CLC. It's on this row of this array, and we know that the immediate command is a good one, but I tried to do something else with it, didn't I? I tried to do, sorry, the accumulator and implied is a good one, but I tried to do something else with it. I tried to do an immediate and it won't let me because it says FF is invalid. So that's how the assembler works out what is a valid and what is an invalid opcode, because it goes along and it goes through that entire process we outlined in the slides, and the return value from here, from this array, specifies whether or not that, that's part of your validity check. So it says, well, actually I've got crap opcode and therefore I can't actually do anything with it. So we can even do sort of fancy stuff. So if we take whatever, so if we do a load for the accumulator, and let's load an immediate value here, and we'll go load an immediate value of 0f. Okay, it's done it. It's incremented this to 3 because it knows that that's a 2 byte instruction. 3 minus 1 is 2, so there's 2 byte instruction. And if we go and have a look at LDA, we could see, probably, let's go find it. So if we go find the LDA in here, it's in there somewhere, there it is. So this entire line here, and we know it's an immediate instruction. That immediate instruction is A9, it's valid, therefore it applies the assemble. And then we can do store the accumulator, and we can do sort of fancy stuff here. So let's do a store 0403, X. Again, it's taken that, it knows that's a 2 byte instruction, okay, and 5 minus 3 is 2, and it's done that, thank you very much. And if we want to terminate the assemble, we hit return. So if we can do one of two things here now. We can disassemble AAA0 through to AAA5. Let's do that. Okay, and now AAA0 is our CLC. We saw that go in, and it's got a hex value of 18. And I think we saw that a minute ago, didn't we? It's up here somewhere, where the devil, the CLC was. There it is, and there's the value of 18 that we got. The LDA for 0F, well, that's an A9 0F, and we saw that there, A9, and the 0F was the operand, and then it's 8103, and you can bet your bottom dollar that addressing mode there for 8103 on STA will match. So if we go STA and go, there's our 81, okay, and if we go up the column there, we can see that it's indirect X, okay. So 8103 tells the it's been assembled correctly. So the assembler is working. And again, if you wanted to see that in memory form, we could memory dump A0 into AA. We do it to AAAF. There we go. And you can see that is exactly what the bytecode in memory looks like. So that's the assembler in an overview form. I don't want to make this video too long, but if you like it, subscribe. If you've got any comments, any questions, then please leave them and ask. But this will probably be the last video that I do specifically about the 6502 assembler, because I'm actually looking at doing some sort of front-end interface for it next, so we can add screen routines and sort of other ROM-based things and make it a little bit more interactive, rather than just having sort of effectively a programmed breadboard, which is what we've got there.